Right, good day. This is Mr. T, section 13.1, honours section for your secondary math 2, complex arithmetic. How do you do? It's good to I'm just kidding. Good morning, good afternoon, or good evening. It's good to have you. Mr. P still here, still doing the honours section. No Australians. Uh, I mean, maybe you're an Australian taking this class, in which case, good day. How do you do? But in any case, let's go ahead and get to it. Complex arithmetic. So this is section 13.1, our honor section of our secondary math 2 guided notes. Might be helpful to review lessons 4.5 and 4.6 before starting in on this one. But hey, it's your life, man. A complex number, a plus bi, has both a real component, a, we've talked a little bit about that, and an imaginary component, bi. It can be represented as a point on a plane with the coordinates a comma b, with the vertical axis representing the imaginary axis and the horizontal axis representing the real axis. Notice the point 3 plus 2i on the axis right there. Okay? So that could be thought of as 3 plus 2i. 3 plus 2i. Now, a vector representation is that it also might be represented by a position vector with its tail located at the origin, 0, 0. Notice minus negative 2 minus I on the axis to the right. Since we are using the horizontal and vertical axis, or a rectangular coordinate system, to represent the vector, we can say that the complex number is represented on the complex plane in rectangular form. So if you were going to represent negative 2 minus I as a point, you would just put a point at negative 2 comma negative 1. And to represent 3 plus 2i as a vector, you would simply draw said vector centered at the origin and pointing at 3 plus 2i. Cool? Cool. Modulus. The magnitude of a complex number, where the magnitude is the length of the vector representation in the complex number. This is represented as, it looks like it says the absolute value of a plus bi, but it turns out what it is that's the length of a plus bi. So find the modulus of the number represented below. So it looks like that goes negative 2. So this number is negative 2 plus 1, 2, 3, 4i. So what this is really asking us, what is the modulus of negative 2 plus 4i? And that's the length of this vector. So what we're going to do to find that is we're going to imagine this right triangle that you could make, where it goes 2 this way for your real, and 1, 2, 3, 4, 4 this way for your imaginary. And we're going to find that length here, which we'll call m for the modulus. So if you use the Pythagorean theorem, that's 4 squared plus 2 squared equals, well, our modulus squared. And 4 squared is 16. 2 squared is 4. 16 plus 4 is 20, equals m squared. Take the square root. And so m is equal to positive or negative square roots of 20. But of course, since this is a length, we don't care about the negative result. I can reduce that because that's 4 times 5, which is 2 times 2. There's your pair. Pull them out. So the modulus here is equal to 2 square roots of 5. That's the actual distance, and I'm actually not going to leave that as m. I'm going to say the modulus of negative 2 plus 4i is 2 root 5, which is approximately, if you do, well, you can just do the square root of 20, which is what we started with, 4.472. That's the approximate length of the vector representation. So I want you to imagine, if you feel like drawing a coordinate plane, who am I to stop you? But I'm going to show you kind of how we're going to do this shortcut-wise. 1, 2, 3, 1, 2, 3, 1, 2, 3. Why 3? Because that's the highest number I see. So 2 minus 3i, 2 is the real part, 3 is the imaginary part. And so the vector in question is here. Now notice that this goes 2 this way, and 1, 2, 3 this way. And hopefully we're starting to notice a pattern that the modulus of 2 minus 3i is equal to the distance, which we can get from 2 squared plus 3 squared equals that distance squared. 2 squared is 4, 3 squared is 9, 4 plus 9 is 13, take the square root of both sides, and again, we're not worried about the negative result. M is the square root of 13. That is, the modulus is exactly the square root of 13, which is approximately 3.606. And that's where I put my box around the answer. I never boxed this answer. Oh, how awful of me. So for adding complex numbers, that looks a lot like what we did before. So if we add complex numbers algebraically, all we need to do is add the real parts. 2 plus -3 is -1, and add the complex parts. I plus 2i, which is 3i, which means that the result is -1 plus 3i. Just combining like terms. Pretty simple. But this one, add a complex number geometrically, is a little bit trickier. So I want to put an axis, and let's see if we can get away with putting it straight down the middle. Okay, so 2 plus I is real 2, imaginary I, right there. There's 2 plus I. Now to add something geometrically, we have this vector. Can I make that head look a little bit? Yeah, I like that one better. There. And we're going to add -3 plus 2i geometrically. That is, instead of starting at the origin and going left 3 and up 2, which is, in fact, what you would do to show -3 plus 2i, we're going to do that same thing, except we're going to start at where we ended our last vector. So right here, -3 is the real part, 1, 2, 3 on the horizontal axis, 2, 1, 2 is the imaginary part, which means that it goes right here, which goes back 1 for its real part, and then up 1, 2, 3 for its imaginary part. -1 plus 3i, the same result. Subtracting works very much the same way. Subtract the complex numbers algebraically. So we're going to do -1 minus 4. That's the real part. -1 minus 4, which is -5. Positive 2i minus -i. So 2i minus -i, which is the same thing as 2i plus I, which is 3i, which gives me -5 plus 3i. Okay, so let's see here. We're going to try to put this right down the center again and see if that works. So join me, if thou wouldst. And so let's start with -1 plus 2i. So -1 plus 2i right here. That was back 1 for the -1 on the real part, plus 2 for the imaginary part. We'll put that in a different color, like purple. There it is. Now we're going to take 4 minus I away from that. And so how we're going to wind up doing that is we're going to go, instead of going right 4, 1, 2, 3, 4, we're going to do the opposite and go left 1, 2, 3, 4. Why? Because we're taking it away. And then instead of going down 1, we're going to go up 1. This is kind of the equivalent of distributing those in there and giving me -1 plus 2i plus -4 plus I. I distributed the negative in there and turned that into some addition, which is -5 plus 3i, which is very much what I was expecting to see. Yepers. How do the addition and subtraction of vectors geometrically explain the addition and subtraction of vectors algebra? I don't think that's correct. How do the addition and subtractions of complex numbers explain the addition and subtraction of complex numbers algebraically? Well, I would say that we are shifting the real and imaginary parts around, right? Like by subtracting, you're just moving things left and down, or up and right if you're subtracting negatives and so on.